Hello, thanks for coming. I'm really glad to see you here. I know these 2 days, they were pretty intense, so I'm really glad to see you alive and kicking. My name is Mykyta Protsenko. I'm a backend engineer at Roku. I work in billing and payments team. And today I'm going to talk about how we manage infrastructure as code using Gradle and Terraform. I'm going to go through the history of the problems we had. I will talk about different solutions we tried, and about the errors we made along the way. And I hope you will leave this talk with a better idea how to automate your infrastructure. When we just started migrating from monolith architecture to microservices, we faced a problem. We needed to provision tons of AWS resources, elastic load balancers, EC2 instances, ECS services, you name it. And we had to do it in different environments, QA, staging, production. And on top of that, we were seriously understaffed. Our ratio of devs to ops was like 7:1, I believe. So let's take a look at the technical scope of the problem. One project on average defines about a dozen of different AWS resources, load balancers, RDS instances, CloudWatch alarms in 3 environments. That's 36. 5 projects means 180 AWS resources, 10 projects, 360, and so on and so on and so on. It keeps growing, it keeps exploding. And first we tried doing this manually. And of course we ended up with a huge mess. Which is worse, the mess was not just technical. The process itself was a mess. Please raise a hand if you ever have been in the following situation. Dear ops, I need to provision 2 VMs and 1 load balancer. Okay. File a Jira ticket and come back in 2 days. We're tragedy. I've been there. Has anyone? Okay, brothers, I can feel your pain. I certainly can feel your pain. So we started looking for a tool to enable developers to provision infrastructure for themselves without waiting for anybody. And first, we tried CloudFormation to describe our resources in some formal way to automate the deployment, and it was a great step forward. We had something we could check in, we had something we could use as a source of truth, but in my opinion, there was one problem. Let's take a look at this example. It describes a DNS entry. There is a time to leave, entry type, there is a reference to a Route 53 zone, there is a reference to EC2 instance, and so on. Sounds simple, right? Does it look simple? Or easy to read? I don't feel so. Don't get me wrong. I believe CloudFormation is great. I just don't feel that it was written to be used by humans. I feel like it was written to be used by robots. Angry robots that really hate humanity. Then we discovered Terraform, and so far it has been a great experience for us. It feels like it's written for humans, by humans, namely by HashiCorp, the company which is already famous for a bunch of other DevOps tools. Is anybody here using Vagrant? I do. Okay, a few hands here. It has great documentation and community. I strongly recommend checking out the website. So let me give you another example. This is the same DNS entry written as a Terraform script. Much easier to read, right? Feel the difference. This is written for humans, and this is for angry robots. Okay, a few more words about Terraform, the geeky stuff. What does Terraform do? Terraform basically allows you to define your infrastructure as easy-to-read source files. These files can be checked in along with your code, they can be shared, they can be reused. So here we have an example of a very simple Terraform script which defines an S3 bucket. The resource type is defined in the first line, then we have the resource name, basically it's just an internal variable name, internal to Terraform, and down there you see the resource properties, and for S3 bucket, the properties basically is the bucket name. For EC2 instance, it can be much more complex. You may need to define a VPC, instance type, availability zones, subnets, stuff like that. And Terraform can take variables to be used as your script's input. These values can be provided through environment variables or through property files. So here we have a modified script that takes an arbitrary name for your S3 bucket. Whatever you provide for the variable, it will be used as a bucket name. Why do we need that? Maybe we want to use different buckets for different environments, right? One bucket for QA, one bucket for staging. And Terraform resources may reference each other. here you may see an AWS Lambda function referencing an S3 bucket we just defined. And Terraform can define outputs, so other projects can reference resources you created. So here's another example. We publish our bucket ARN so other projects can define their own lambdas to use this bucket. And you can organize your scripts in multiple files. Terraform will pick up all the files with .tf extension, and it allows you to organize your resources by type. For example, you may put all RDS-related resources into one file, all CloudWatch alarms into another file, and Terraform is smart enough to build a dependency graph and provision your resources in the right order. Two main Terraform commands, your daily bread and butter, are plan and apply. If we use our sample file that defines an S3 bucket, if we provide a value for Terraform variable, and if we run Terraform plan, we'll get a list of pending changes here. You can see we're about to add an S3 bucket. We can inspect the properties of this bucket before we actually proceed. OK, sorry. OK, good. So when we try Terraform apply, we actually provision our infrastructure. This step will also update your Terraform state. What is Terraform state? Terraform state basically a map between a real-world resources and your configuration. Basically, it records what has been provisioned already. So if you change your script, only the delta will be provisioned. Basically, if you run Terraform apply using the same script again, no changes will be made. If you describe another bucket in your script after you already deployed it the first time, only the second bucket will be created next time. The problem here is that your state is stored locally by default. Why is that a problem? Well, what if you accidentally delete this state or change it? Or worse, what if somebody else wants to deploy infrastructure changes using your configuration? They do not know what has been provisioned already. Basically, the question here is, how do you share the state? Fortunately, Terraform provides a mechanism for that, a remote state, to make sure that your state is stored remotely, for example, in an S3 bucket, and accessible to other projects. You need to configure it explicitly using this Terraform command. Terraform provides a range of available backends. You can use console, you can use Git, but we ended up using S3. After all, we already hosted everything else in Amazon, so it was an easy choice for us. So let's go back. Now, when we know what Terraform can do, let's see what kind of solutions we tried building here. We wanted to build a tool that gives power back to developers. Don't forget, we were seriously understaffed on the infrastructure front. We wanted to make sure that developers had tools to provision infrastructure they need without waiting for infra team. We didn't want infrastructure team to become bottleneck. Instead, we wanted to shift some of their daily tasks to developers. But scaling developers is hard. Scaling humans is hard. So we wanted to automate everything that could be automated and make sure that developers have something that is powerful but reasonably easy to use. We wanted to minimize deployment time. If the process takes more than a couple of minutes, it becomes a burden you want to avoid. Developers will try not using your tool if it is slow. The whole effort will be wasted, so minimizing interaction was an absolute priority for us. And we wanted to provide a safety net and some level of oversight. After all, Terraform is a really powerful tool. It lets you make mistakes 1,000 times faster. We wanted to make sure you don't go ahead and provision 300 of EC2 instances instead of one, for example, or delete a security group, and finally, your services cannot talk one to another anymore, right? We wanted to sort of have a safety net here. Basically, we wanted to have a tool that will, A, configure Terraform remote state in a S3 bucket using the best practices, making sure it's encrypted, then do a Terraform plan so we can review the changes and have our safety net there, and then do Terraform apply to actually provision the infrastructure. Now, when we had our Terraform process defined, we started thinking about it, integrating it with our build system. Gradle was an obvious choice for us, after all. We already used it to build our Java code. It worked really well. It took us a few iterations to figure everything out. And I believe we're still not at the end of our journey, but so far it worked pretty well for us. So let's take a look at what we actually did, which stages we went through. At first, we implemented a very naive solution. We checked in the Terraform configuration scripts and the shell scripts to run to manage Terraform state and to run plan and apply command. And we added Gradle tasks to run these pre-configured shell scripts. What's wrong with this picture? Right, if you have to change something, if you need to make an adjustment to your S3 state management logic, you need to go to all of the projects that are out there and make the change in each and every of them. Fortunately, we caught this problem early enough when we just had 2 or 3 projects using this approach. So the next obvious step for us was to set up a Gradle plugin. We wrapped the Terraform management shell scripts in a Gradle plugin, and by using Gradle dependency resolution mechanism, we made sure that you can get plugin updates when you need them. If you need to update it, you can just change the version, or you can use dynamic version resolution mechanism of Gradle to get the latest and greatest stuff. Let's take a look how it works. The plugin provides Terraform task type, which you can configure to reflect your project needs. So here we have a directory with our Terraform scripts. We have a file with environment-specific configuration, so you can actually provide values for your Terraform variables. We have action, plan, or apply, which we can read from the command line. And finally, we have our remote state configuration saying, OK, we want to use this S3 bucket, we want to use this S3 key, we want to use KMS key to encrypt this stuff. So here's an example. Let's say we have our Terraform script, which defines an S3 bucket that we just reviewed a little bit earlier. And after running this Gradle task, you will get this result. It says, OK, we're about to create one S3 bucket. And it calls Terraform plan under the hood. And the whole thing looks very similar to a regular Terraform plan. This is done on purpose. We wanted to minimize the interaction. If you know Terraform, you can just use it. And after you're done reviewing the changes, you can apply them with this Gradle task. And voila, the bucket is created. And the fact that it's created is recorded in remote Terraform state. It worked fine, right? The problem here was that it required Terraform to be installed on each and every box involved. And you needed to have the right version of Terraform. You needed to make sure that Terraform binary is on the path. It was basically a maintenance hell. And we ran into this problem when we tried to use a new feature of Terraform. We just came up with one of the latest versions. And oops, we needed to upgrade a bunch of Terraform instances on a bunch of boxes. Fortunately, it was easy to do. All we had to do is to fix the plugin. And yep, the next logical step was to make sure that Terraform itself is managed by Gradle as well. We added a couple of configuration options to make sure that we can install the exact version of Terraform exactly where we want it. The plugin checks if it is there, and if it's the right version, and if it's not there, it will download it and install it into a specified directory. And it doesn't download the same version twice, so you don't have to worry about bandwidth usage or build speed. And basically, it makes sure it doesn't matter when you run your build. Developer boxes will have the same version as your Jenkins slaves, for example. Gradle plugin will take care of that. So I did a lot of talking. So let's see if this stuff actually works. Talk is cheap. Show me the code, right? OK, so I cheated a bit. I wrote my code ahead of time. I checked it out. So let's start, and let's see if it actually works. So let's start with build Gradle. OK. So at first, here we have a Gradle plugin being configured here. And we have a Terraform task defining our Terraform. So basically, we're saying, OK, we want to use Terraform scripts from directory called Terraform1. We don't want no variables to be defined here, just an empty file. We want to read TF action, plan, or apply from the command line, and this is where we want to store our remote state. And so what do we have in this Terraform1? We have a file called S3, Terraform1. It's pretty simple. Basically, we're saying here, OK, we want to provision our stuff in AWS. And the stuff we want to provision, basically, we want to create one S3 bucket called demo1 and Protsenko bucket. We want to use US West 1. That's because I'm a cheapskate. This is the cheapest region in AWS. OK, so let's give it a try. Gradle W. The task name is Terraform. And let's specify the TF action option equals plan. OK, at least it's doing something. It's initializing the remote state, and yeah, it says it's about to create one S3 bucket. So, oops. So let's make sure the bucket name is demo1, the region is the right one, so it looks good. We can proceed. Let's actually do apply. Let's actually create this bucket. Oops. And I'm using the bucket because it's like the fastest AWS resource to create. If I was using EC2 instances, it would take like a couple of minutes to create it, start up. So I'm just picking up the smallest resource for the sake of demo. So OK, creating. Since it's like California, it's going to take like 20 seconds. Still creating. Oh, voila, it's there. Let's make sure I'm not cheating here. Let's take a look at our AWS console. OK, we used to have 2 buckets here. Let's refresh this guy. OK, demo1 bucket is here. It actually created something. So you see, you can create your resources as needed. All you need is to write this thing. OK. And Terraform is evolving fast, so our tooling had to evolve along with Terraform itself. And recently, Terraform has added a few notable features like remote backends and state locking, and some of the existing features became mature enough for us to start using them. So let's talk about these new features. Let's start with modules. What is modules? Modules basically is a Terraform way of organizing and reusing common pieces of your infrastructure. You can think of them as of sub-projects, as of Terraform sub-projects. For example, if every microservice you have needs a RDS instance and a CloudWatch alarm for CPU usage, then instead of copy-pasting code, copy-pasting Terraform code and putting it in each of your projects, you can pull out these definitions, these Terraform definitions, and put them in your module and reference them in your projects. And modules are configurable, similar to regular projects. They can define input variables and outputs. So if you want to configure different threshold on your CPU alarm, you can do it using your input variables. And while Terraform provides quite a few options for storing modules, of course, S3 bucket is an option. The best way, in my opinion, is to store them using Git. Terraform supports Git as storage, and it can leverage Git tags as well. So you can use Git tags basically to version your modules. And if you reference a Git tag in your Terraform module usage, then you get exactly the version you need. You don't have to worry that some backwards incompatible change will break your configuration. But if you want to use the greatest and latest stuff, for example, if this module is internal to your organization, just skip the tag part and always get the latest stuff. It's up to you. But the trick here is that before running any Terraform command for configuration that uses modules, you need to run Terraform get first, so it can download and import modules used by your configuration. It has to go out and pull them before you do anything. OK, and the next thing I wanted to talk about is remote backends. As you remember, to create a remote state in Terraform, we had to run this command. That was not very convenient, because we had to provide this command a lot of project-specific data, like where to store the remote state, how do we name our bucket. And it also created a tight coupling with S3. It wasn't a problem for us, because we were already using AWS for everything else, but it prevented any experiments with other backend storage mechanisms. Developers actually started complaining about that. Fortunately, Terraform 0.9, I believe, added a very useful feature, remote backends. So now, basically, you can define your remote state as a part of your configuration. You can say, I want to store the remote state in this bucket, using this key, using this region. So we're still using S3 remote state, but now we can experiment with other solutions. We are no longer tightly coupled to AWS. And the primary motivation for these experiments was that some of the remote backends supported lock-in. Basically, lock-in is a way to make sure there is no race conditions. Basically, you can protect yourself from a situation when two developers try to deploy infrastructure changes simultaneously, stepping on each other's toes. You want to avoid that. And an interesting thing here, if you want to say, OK, I don't want my bucket to be defined here, you can skip it. Partial configuration is supported by remote backends. Then you will need to provide a couple of command line options to make it work as a part of Terraform init command. And yes, if you use remote backends, you need to run another Terraform command before you do anything else. You need to say, OK, Terraform, please instantiate my remote state, and then you can proceed. Fortunately, this command is idempotent, so you can run it multiple times safely. So we decided, OK, let's put it into our Gradle plugin. It will take care of it. It's a small overhead, but it makes things safer, so you don't have to think about it. And to enable all this goodness, we had to provide developers access to Terraform commands we just reviewed, Terraform get, Terraform init, and much more. There is a ton of Terraform features that you may or may not need. And we decided, OK, it's not our call to tell developers what to do. We just wanted to replace this flow that we had already, which is configure Terraform remote state, put it into S3 bucket, create tie couple into S3, do Terraform plan to review stuff, do Terraform apply. OK, this approach didn't work for us anymore. We had to replace it with a new flow. So we wanted to, install Terraform, make sure we specify the Terraform version, so we had the right set of features. The plugin had to take care about installing Terraform before we do anything else. We got rid of enforcing remote state policy through the plugin. Now we can define our role or backends. We were not limited to AWS storage anymore, though the plugin does make sure that remote state is instantiated before you do anything else. And the command itself now is an arbitrary Terraform command, no longer limited to plan and apply. So you can leverage the full power of Terraform. So here is an example of a new Terraform task configuration. We define a Terraform version first. Then we say, OK, this is the directory. This is the folder with our Terraform script. This is our Terraform action, which is an arbitrary command now. It can be anything you want. And as you can see, we can still use partial configuration. We can still enforce the policy, but now it's configurable. Now you can say, OK, I don't want S3 anymore. I want to replace it with some Google storage policy. And it will just work. Just put all the externalized part here into TF init params, and it will work. So now instead of this huge manual mess or scripts written for angry robots, we had this nice build flow. The init command was done automatically under the hood. The regular flow was like, do the plan. If there are any changes, let humans review it. Let's make sure there is a safety net. We don't break stuff. We don't spend too much money on something. And then do apply. And if we had to customize it, we had the ability to do so. So for example, if we wanted to use configuration that used modules, let's do Terraform get first, and let's do Terraform plan to review the change, then do the review, then do the apply. It just worked. We also considered leverage Gradle task dependencies to make sure that the build scripts are executed in the right order. But so far, we're still not sure that we know what the right order is. So we decided to just give this power back to developers. If they want to use it, they can just add this Gradle depends on parameter and say, OK, I want this task. After this task, I can have multiple Terraform tasks defined. Nobody prevents developers from doing this. So this option is on the table. So I've talked about a bunch of things. So let's see if they actually work. Let's do a second set of our demo, second part of our demo. OK, let me continue my cheating and see what I have here. Let's go back to build Gradle. OK. So it looks a little bit different now. So first of all, I'm using newer version of the plugin. And the Terraform command looks differently. I'm saying, OK, I want to use newer version of Terraform, 10.6. I want to put it into OPT Terraform. And all I care about is tfdir and tfaction. And init parameters is kind of optional here right now. Basically, what I'm trying to say here is let's keep any interactive input because you don't want interactive input when running build commands. And let's see what we have in Terraform 2 directory. It's S3. OK, this thing looks different now. It says, OK, I want to store my remote state in this bucket, in this key, in this region. So it's self-contained now. We don't rely on anybody else to define the remote state. And the second two things, the second two resources are the same. We're still saying, OK, it's AWS, and it's the bucket, and the bucket name is demo2. OK, let's give it a try. Start with a plan command. It's setting up the remote state. It's doing it differently now. So now you can see we have this 10.6 we use it explicitly. OK, and there is one resource to be created. Yeah, demo2, US West 1, all the right parameters, so it's safe to actually go ahead and apply the changes. Again, it's going to take like a minute. It's applying, synchronizing the state. I don't know if I can blame Wi-Fi. Probably not. OK, creating the right stuff, the right demo name, the right bucket name, I mean. OK, creation complete. Let's check it out to make sure it works. We should have 4 buckets now. OK, but now we have the full power of Terraform. So I don't want to pay for this bucket any more than I need to. So I want to destroy this bucket as soon as I created it just to save on some cost. So, and how do we delete stuff? By using destroy commands. Destroy Terraform command and adding -force to prevent interactive input. And it could have been any eligible Terraform commands here. It just passed as is. OK, again, this is something that takes time. Unfortunately, the infrastructure is slow. All infrastructures, OK. And yeah, destroying stuff is faster than creating stuff. That's good. OK, let's make sure it's actually destroyed. Let's refresh this guy. Yep, it's destroyed. It works. So now the final part is modules. Let's make sure that modules actually can do everything we're talking about. So again, build 3. So the build script is identical. It's the new version of the plugin. The only difference here is the tfdir command. It references a different folder. So let's see of what actually is there in this folder. And it does look differently here because we still have the backend and we still have our provider. This thing is identical, except the key in which the backend is stored. But we no longer have AWS bucket resource defined here. All we have is just the module saying, OK, somewhere on GitHub, there is a module, so let's just take everything in this module and create this, and then let's pass it some parameters, namely the bucket name. So let's see what's in this module, actually. OK. OK, and in the module, we have our variable defined, because it's just a sub-project. It's a legit Terraform script. We have our S3 bucket defined. And OK, let's say I can take in any bucket name and just pass it as is. And the thing here, we have defined an S3 usage alarm because, again, as I said before, I'm a cheapskate. Like, if somebody tries accessing this guy during this demo, I want to fire an alarm saying, OK, if I have more requests here than like 50 requests per minute, I want to trigger the alarm. And we are referencing the actual AWS bucket resource that has been defined here. So we have a full-fledged Terraform configuration, basically externalized. And so when we run to plan and apply, we're going to create two resources instead of one, and they should be created in the right order because you need to create an S3 bucket first and usage alarm later because it references the bucket. So let's give it a try here. OK, it should show us that two resources are about to be created. And it's going to take even longer. Sorry about that. OK, it was actually pretty fast. So we have our bucket, and we scroll up, and we have our CloudWatch alarm. The parameters are right. The metric name, spirit, statistic thresholds, they're all here. Let's create this stuff. OK, now we should see the bucket being created first. We want to make sure that the dependency graph is working as it's supposed to. OK, bucket is being created, not the alarm. That's good. OK. Daddy, are we there yet? OK, and now the alarm should be much faster. Yes, everything is complete. Let's make sure. Let's refresh the S3 page. OK, the third is created. Let's make sure we can destroy them both, right? Because after all, we have referenced a model, and like, let's make sure that when the configuration with the model is used, it just behaves as a regular one. Destroy dash force should be faster. OK. Refreshing the state, basically making sure that these alarms are there to be destroyed. OK, make sure the bucket is there, alarm is there. Yeah, and please note that destruction is done in the reverse order. That makes total sense. Final check, really the final check this time. OK, it's gone. Good. So now back to business. So we covered a lot of technical issues here, and I actually had a question about human participation in this process before this talk. And yes, the final problem we had was humans. Not all developers like to maintain infrastructure themselves. You're going to meet resistance if you want to introduce this process, because developers may be like, I just want to write code, I want to pack a jar, I want to throw it over the fence, and I don't care about it. This desire is understandable. Any change produces resistance. But if you want to write scalable code, the code that really works and really scales, you need to understand your limitations of your infrastructure, so you need to know your infrastructure. Code doesn't live in vacuum. Don't be this over-the-fence developer. And maybe you say, OK, cool, I don't want to be this developer. I want to understand what's going on. I want to know my infrastructure. But learning infrastructure is hard. AWS documentation is huge. Terraform documentation is a little bit smaller, but only a little. The whole process may scare you. especially if you have never done anything like that before. Luckily, there is a solution to it, maybe not a solution, but at least a way to build a bridge to ease this pain. Amazon has invested a lot of effort into AWS UI. It used to be like really bad. It got much better recently. And UI is much better, much easier to navigate and learn than code or Terraform scripts. There are wizards in UI to guide you through the process. Basically, you can go and say, OK, there is a CloudWatch metric. How do I create one? OK, there is this window. I can click this. I can click that. There is a name. There is this parameter. Oh, cool. Like, I start to understand something. But UI doesn't scale. You don't want to click these buttons in the gazillions of your environments for all your resources. Fortunately, you can build a bridge between AWS UI and Terraform. So you can start experimenting with AWS UI, start creating your resources. Maybe you can build a prototype. And you can export the result of your experiments into Terraform script. There is a project with a very silly name. It's called Terraforming. It's really easy to miss because like you start it and you get the link to the regular Terraform part. However, it works just fine. It lets you convert basically anything that you created manually into a Terraform script. It works wonders. You just specify the kinds of resources you want to export. For example, I want to see everything that is related to S3 buckets. And you just get a list of your resources of this type already wrapped in a Terraform scripts. Maybe you need to edit this script. Probably you need to edit this script because you don't want to have like a hard-coded bucket name. Maybe you want to have a variable that replaces this bucket name. Maybe you want to have a reference to another Terraform resource that you defined it earlier somewhere else. But you have the power, and editing is much easier than creating things from scratch. So let's take a look at the final demo. I believe we have like 2 buckets left, right? The one from the first demo and another one that stores everything, all the remote states. So let's do terraforming S3, right? And it should be much faster because it's not creating, it's just reading state. And voila, yeah. And this part look familiar because that's just Terraform script, similar to what we had in our example. Yep, this is it. So to sum it up, let me share a few tips and tricks that we learned along the way, and I hope this stuff will make managing your infrastructure easier. So first of all, if you want to manage your infrastructure as code using Terraform, please set up a remote state in all your projects. Latest Terraform versions support a wide range of possible backends from console to S3. Basically, it doesn't matter where you set it, just please set it. And some of these states, they support lock-in to prevent race conditions, prevent developers from deploying infrastructure changes simultaneously. This is a lifesaver. So if you want to try use this feature, please go ahead. It will really make your life much better. Put safety first. For example, if you use S3 for your remote backend, please make sure that the S3 bucket is versioned. This way, you can always go back to the latest good version of your remote state. If something goes wrong, if you break something. If you use Git, you just get it out of the box, Git's greatest version and stuff. And please set up a change review process. Terraform is really powerful. You have to use it wisely, because infrastructure errors may be very costly. It may be like the most expensive error you ever make. Like you can totally bring the whole system down if you screw up. And I cannot emphasize enough the importance of running a plan command and reviewing the results before applying any change, no matter how small. Besides regular changes, please watch out for A, deletions. Make sure you're not breaking anything, you're not deleting, make sure you're not deleting resources accidentally. The most common reason for that kind of breakage is changing a resource name. You think, oh, it's easy to change a resource name, but some of real-world resources cannot change their name they have to be recreated. It means you have to delete the resource itself and create it again, and probably you need to delete a resource that has a dependency on this resource. So like this part can literally break your whole system, so please watch out for it. B, please watch out for extra costs when adding your resources. For example, you may want to make, if you have a cluster or like auto-scaling group, you may want to make a default number of instances configurable. Like you may want to have 25 instances for your production and 1 instance for a QA environment. Or watch out for DynamoDB provision capacity, read and write capacity, so you don't pay extra for the stuff that you don't use in environments like staging and QA. And the third point is related to safety, but it's important enough on its own. Basically, what is it about? If you want to make your infrastructure more robust, you may want to set up a separate project to configure your most critical infrastructure parts like security groups, IAM policies, VPC, network configuration, stuff like that. Then you can define a project-specific infrastructure in the project itself. If we're talking about containerized deployments, we usually talk about a load balancer, a task definition, an ECS service, a few CloudWatch alarms, maybe an RDS instance or DynamoDB table. You just put it along with your project. This way, if you make an error in your project, you're not breaking the whole system, you're just breaking your project. It's making the rest of the system more robust. Also, you may want to make the review and release process for your core infrastructure project more strict. Think nuclear launch codes, like you may want 2 people to press the approve button before you make any change to the core project. And to make your builds debuggable, you need to make them repeatable. The way to make it is to make sure that your build system is not calling Terraform directly, that it's referencing instead your Gradle tasks and dependencies. Make sure that all inputs can be provided as a command line arguments or environment variables. We have tried providing stuff in property files, but it proved to be cumbersome and not secure. So environment variables and command line arguments is the way to go. And make sure that build system calls Gradle Terraform task, because by the end of the day, calling Terraform task through Gradle is just a line in a shell script. And this way you can easily debug any issues that you may have on your local box, because you don't have to wait for the Jenkins build to complete. You just run the same Gradle task, providing the same inputs, and voila, you're ready to go. And if you do this, you can use any build system, Jenkins, Travis CI, TeamCity. It doesn't matter where you run it as long as it has the same inputs, because it's just a bunch of shell commands. And this is all I have to share for today. So if you're interested in managing your infrastructure as code, here are the links you may find useful. The first is the link to Terraform site itself, has great documentation. Please check it out, it's really cool. The second is the Gradle plugin I was talking about. You don't have to use it. Just take a look at it, maybe use it as an inspiration for your own process, because your process may be different from what we had. But if our process works for you, take a look. It's totally worth it. And the final link is the link to this terraforming command that let you build a bridge between AWS UI and Terraform. You can start exporting your experiments right away. So we still have some time left, so if there are any questions, I'm totally willing to answer them. Thank you.
Thanks for talk. Actually, we are using AWS in production, so we have a bunch of resources created with CloudFormation. Is there any option to migrate it to Terraform without deleting it?
That's a great question. Actually, there is. Terraform itself has a command called import. Basically, every resource that is out there can be imported. You need 2 steps basically there. First, use this terraforming helper script to help you with your resources, so you don't have to write them from scratch. And B, run this terraform import command. Let me actually show you something. So, I'm totally dependent. I always do this Google-driven development. So let's say Terraform S3 bucket, right? Maybe there is an S3 bucket you want to import. We have this link to Terraform documentation here. Let me make it a little bit larger so it's readable. So we have this documentation. We're going to skip it, because like, it has everything: login, object lifecycle, terrific, replication. OK, I didn't even know this thing existed. OK, so we have arguments reference. But the thing I wanted to show that at the end of every Terraform resource, there is a description how to import this specific resource. Because for some of the resources, you may need to use a resource name, like a bucket name. For some of the resources, you need to use ARNs, these long strings. For some of the resources, you may need to use some custom identifiers. Terraform understands that, and each and every of these resources have a helper import command and documentation to describe the importing process.
Thanks, and one more question. Actually, you told us about different modules in Terraform, and you know, in CloudFormation we have stacks. And it's impossible to move resources between stacks. You can only delete it from stack, but keep it somewhere. But you can't add existing resource to stack. So is it possible to, should the modules in Terraform correspond to stacks on AWS?
So let me repeat it to make sure I got the question. So can we make sure that Terraform modules are actually connected to CloudFormation stacks to make sure?
No, actually I want to have different CloudFormation stacks and Terraform modules that do not correspond to the structure of that stacks.
Yes, you can, because Terraform module is arbitrary. You can totally define everything you need there. This stack, I believe, is something different.
Hey, thanks for the presentation, first of all. The question is, apart from being cloud agnostic, I guess, with Terraform, what are the other benefits that you notice and you make use of in your project?
The question is about being, wait a second, I want to make sure I heard you right. So the question is about being cloud agnostic and what the other things about the other cloud providers, right?
Like comparing to CloudFormation, for example, have you compared different solutions, and apart from being agnostic?
Yes. We tried CloudFormation.
It's a very general question.
Yes. So we tried CloudFormation at first, right? It worked really well. The problem with CloudFormation, as I said before, that it was hard to maintain for us because JSON is written for automatic parsing. It's not written for humans. What are other stuff that is out there, like Chef and Ensemble? It's not about actually managing the infrastructure itself. It's more about managing the state of this infrastructure. So I believe Terraform is a kind of standalone solution. And CloudFormation is not cloud agnostic, by the way. It's tightly coupled to AWS. So yeah, I believe, yes, we tried different approaches. Terraform worked the better of them all so far for us.
OK, do you use it for anything else? Like, for example, managing GitHub accounts or something like that?
Can you repeat this, please?
You can use Terraform for pretty much anything. You can manage your GitHub accounts, for example, with it, or something like that. So do you use it across the whole platform for everything that can be automated?
Yes, basically in our team, we use it for everything, starting with VPC, starting with the general environment network, the stuff we live in, and ended up with individual services. I believe the interesting question is what we don't use it for. We don't use it for the resources that do not belong to our organization. Like GitHub accounts, we don't use to manage it because I believe don't manage, you shouldn't manage what you don't own. Because we don't want to accidentally break stuff there. We want to draw a line and say, OK, this is the stuff that we're responsible for, and this is the stuff that you are responsible for. And if the cloud team, if the team responsible for maintaining GitHub, the corporate GitHub account wants to use Terraform, it can do this. But I strongly believe that this Terraform script should be different and isolated from the stuff that actually manages our production system.
Thank you for great talk. So my question is, did you use any protection policies to reduce human factor? To disallow somebody to create just 300 instances in Amazon?
Okay, so first of all, we have this review process. So like we have several.
It's again human factor.
Yes. So we have few Jenkins jobs, right? Like you commit your stuff. It runs Terraform plan. It sees are there any changes. If there are no changes, like don't need to bother. We just proceed with compiling, testing stuff, deploying it to cloud, running integration tests, stuff like that. But if there is a change in your Terraform, a change in your infrastructure, then we actually have our infra team paged, because like you cannot get off infra team, after all, they have the expertise that developers might not have. So we call them, and they actually the ones who press the button, who says, okay, I approve these changes. They take a second look at the actual output of the plan command, which is basically a way, like the substitute for code review of Terraform scripts.
Then what was the reason to wrap the Terraform with Gradle? Why not just use plain bash scripts, for example?
It's a good one. We did the bash scripts, but if you want to change the bash scripts, you need to change them somewhere, right? So yeah, you can.
In centralized repository, for example, with control of these guys who know how to do things right.
It's totally possible. It's doable. It might be actually preferable if you don't have a centralized Gradle build pipeline. For us, it was easier because we have this centralized pipeline already, and basically it was better than telling new hires, okay, but please remember there is this centralized repository there that you have to download your scripts from and install on your local boxes, or, well, we were basically like, somebody had to create a script to automate it. It could be a Vagrant script to build some base image that developers run. That's possible too. That's the solutions that people can use.
Okay, thank you.
Hey, thank you for great presentation, and my question is following, maybe a little bit off top. I guess you mentioned you use ECS.
Yes, we do use ECS.
Yeah, and the question, are you happy with ECS and Terraform combination? Because we know that Terraform has a little bit of dark side, because it's Terraform feature that doesn't know, not follow OS features sometimes.
Well, actually, there is a really interesting question, because in my experience, Terraform actually beats CloudFormation in terms of the velocity of changes. Like when we had a placement policy added to ECS, it was actually implemented in Terraform faster than it was implemented in CloudFormation. So Terraform actually looks pretty cool here, because usually if you have a change there, it's released in a matter of weeks tops, right? Sometimes a few days, like 10 days. Like it was really awesome for us so far. But the ECS part is a pretty cool question. I want to elaborate on that. So there is a dark side of Terraform. Basically, you define what you want to do, and if you change something manually, then Terraform tries to revert it. And it's really important in ECS world, because you'll be doing a lot of deployments that will change the state of your service. So you want to make sure that Terraform won't revert your task definition to the very first task definition it created. Fortunately, it can be done. Like there is a feature of Terraform called lifecycle, and there is an ignore part. So what we are ignoring there in the ECS service definition is the task definition reference, because we understand we're going to be deploying tons of new task definitions and updating the service, and we don't want Terraform to be a part of it. And we want to ignore things like instance counts, because we are the autoscaling and we don't want Terraform to downscale. So if there are any parts of infrastructure that are changed on the regular basis as a part of your regular deployment or maintenance process, please make sure that these parts are ignored by Terraform, so Terraform doesn't try to change them again when you do the next deployment.
Okay, thank you. And another question is total off top, so you can skip it if you know. What was the reasons of choosing ECS over, for example, Kubernetes, except of DevOps capacity?
Well, actually, we wanted to go with Kubernetes originally. That was our desire. By a year and some ago, Kubernetes was in no shape to run on AWS. For example, it didn't have the ability to run on private networks. And it was totally inaccessible for us because we're doing billing. We have a lot of outbound calls to banks and like financial institutions. And some of these financial institutions want us to whitelist our IPs. They want us to provide the list of IPs we'll be making calls from. And with public subnet, it's not possible because we scale, we create new stuff here. We want to use NAT, but to use NAT, we want to put our stuff into a private cloud, into a private subnet. And back then, Kubernetes wasn't able to do that. So we said, OK, screw that. We need to use ECS. But today, Kubernetes is mature enough to run on AWS. I believe the only issue it has is some issues with elastic block storage. But other than that, it's pretty good. It's like you can start using that. Basically, in this case, the only reason you need to run Terraform is that you want to provision a base infrastructure like subnets and security groups, and the rest Kubernetes can take care of, like creating load balancer, creating services. Like you can simplify stuff greatly.
Okay, thank you.
Okay, I believe we are out of time. So if anybody else has questions, please come find me. And thank you for your participants. It was real fun to answer your question, guys. Thanks.